other one, what they were touching looks like basically a oval, and well, really a square.
Which is sort of, the surface area actually should not have any impact unless there's a different type of surface
Okay.
along that path. All right. Hoop and ball. Solid ball and hoop. Or we can actually, since we got the fancy ones here, diameter is about the same, radius is about the same. This mass seems more. So this is the race right now. So hoop and sphere. Hoop and sphere. Sphere. Hoop. And no one thinks it's a tie.
I'm confident in my answer this time.
Could make for a really cruel practical physics exam.
There's no way it's a tie.
No, there it is. Ball definitely won that one. We flip around the direction. Thank you.
Yep.
Three, two, one. All right. So, ball won. Congratulations to 5 of you. Why?
It has, I guess it has a greater mass. But that doesn't make sense for the small and the large one.
It's a larger moment of inertia. Is that
The ball would, I suspect that the moment of inertia is actually bigger on this one. I don't know what the mass is. It'll stay up there. It's more mass than it can handle. So,
Yeah.
the mass is gonna be greater than, more than 4 times that.
Okay.
The radius is about the same. This is gonna have a 2/5 sitting in front of the formula. I think we can safely say that the moment of inertia of this is bigger than for the hoop.
Would we just say that that's like basically 10 kilograms?
I would have gone for 1, but.
1 kilo.
the-
Oh, yeah. 1 kilogram.
All right.
My bad.
So, but remember, the greater the moment of inertia, the harder it is to, get it to move.
Yeah.
But this has a larger value though. The disc had a larger moment of inertia than the hoop did.
So it has to deal with once it's moving and how fast it's gonna go at a specific moment.
If they started out already moving, I think from what I'm hearing you say, I think you have a legitimate argument, but the fact that they both start at rest, I think sort of kills what I heard you say. All right, so let's take a look at, we did the race of disc and hoop, and disc won. This is 1/2 mr squared, and this was mr squared. We did small ball and large ball. That was a tie. And that was 2/5 solid balls, 2/5 mr squared. And then we did ball and hoop.
Ball one.
This is 2/5 the ball one, 2/5 mr squared and mr squared. Hoop. Hoop. Ball.
had the ramp been longer, would the larger ball have won the race between the 2 balls? Or will it always be a tie?
It should always be a tie.
Because the equation's the same
Right.
for the moment of inertia.
That's so strange.
All right, so if I did disc and ball, I don't think I've done disc and ball yet. Disc and ball.
it would be the, ball. Right,
I think so.
Ball.
Because it has to do with the coefficient.
because the disc would have a half,
Yeah.
whereas the ball's at 2/5.
3, 2, 1.
The ball is picking up steam at
Yeah,
that
it looked
point.
like it took a little bit of a
Switch directions. 3, 2, 1, go. So the ball was slightly ahead. So Anna, what was the last thing that you had said? Thank you.
It has to do with the coefficient.
It does. Ultimately, coefficient of 1 there, 1 there. The lower coefficient wins. It's not the mass, it's not the radius, assuming that, we are nice ideal, no slipping kind of thing, it is the coefficient up front. So the question is, why? Why is it just the coefficient that matters and not the mass and the radius?
because of the distribution of the mass of the thing that's rolling.
And that definitely affects the coefficient up front.
Mhm.
But if we think about this, there's a lot more mass that is closer to this axis of rotation there than there is for this one. So if you think about just spinning this one, yeah, it had a higher moment of inertia, so technically it required more force, but then again, it also weighs more. The gravitational force actually is the thing that's causing it to roll. Because if I have assume that is straight, and I have something on it like that, the point of contact is right there, the gravitational force is just slightly off of it. There is torque being applied. The greater the force, in this case, so if I had two that were the same size, two balls of the same size, but one was denser than the other, the one that's denser has more weight, therefore more force, therefore more torque, but it's also more to try to get to roll. And that part balances out that they're the same shape. I'm gonna do a slightly different point of view. As it's rolling down, we have normal force, we have gravitational force, and we have friction. Friction doesn't do any work because it's not sliding. That for the reasons we've dealt with before, because the displacement where the friction is acting is perpendicular to the actual friction. Normal force is not doing any work. The only force doing any work is the weight, gravitational force, which is conservative. Energy is conserved. So we start out with both of them with some amount of potential energy. At the bottom, if we assume H is equal to 0 at the bottom, it's all kinetic at the bottom. I have two types of kinetic involved here. One, I have this thing spinning. So I've got this 1/2 I omega squared. I also have the whole thing actually moving down the ramp. So there's a 1/2 mv squared. I have both things involved here. Part of it for spinning and part of it for the translational motion. The more energy that goes into the spinning, the less energy there is to get it to go down the ramp. The higher the fraction, the larger proportion needs to go into this, which means there's less energy left over for that.
So would you say inertia, is that what that is, the I? Is
Moment of inertia.
Moment of inertia is inversely proportional to the, that would be kinetic energy?
Be careful about that. What we're dealing with here is the fraction.
Right.
And I haven't really justified the loss of mass and radius, why they don't matter. And I'm gonna zip it up really quick right now. Monday, next Monday, I'll go into a little bit more detail.
Okay.
So if I have, the fraction up front, I'm just gonna make the letter K. No, some letter I'm not using much, Q. I'm not using Q for anything. So I have MGH, is my potential to start with. And then at the end is all kinetic, so I got 1/2 K, just said I was gonna use Q, Q mr squared plus 1/2 mv squared. Mr squared omega squared R squared omega squared,
Velocity squared.
speed squared. So I'm left with Q over two M V squared plus 1/2 M V squared.
You're just left with Q.
R has disappeared. I have mass in every single term now, mass goes away. And so we end up with Q plus 1 over 2 times V squared is equal to GH. So the larger Q is, the smaller V is.
Okay,
So not exactly inversely proportional, which is
yeah,
And the Q is
the fraction,
the quotient, okay.
which relates to the distribution of mass.
Right.
Now, one thing I have not laid out here, another thing I have not laid out here. What's the actual axis of rotation? If I have the ramp and ball sitting on it,
well,
It's the point where it touches the ring.
yes. And yet somehow I'm making the claim that I got these things going on. That will wait.
so would you say that the axis of rotation is constantly changing for the disc, or would it,
Yes, it is constantly changing.
okay,
It's always the same magnitude, because since the disc itself is like consistently sized, it's always the same distance from like the center of the disc.
And yes, that too.
okay,
But it does involve parallel axis theorem. It'll come out really nicely. I can keep going. I have no problem with that.
No, I get you.
yeah.
We won't do it because Ian can't stick around.
I've gotta leave by like
I gotta
30
get to work.
to get some tutoring.